to give a brief introduction about the Easy language.
So let's start with an explanation to why the name Easy. Most of the programmers have this common question: why does this language has to be so complex? And of course, we had it too, and that's why we wanted to develop a simple and easily programmable language. And we came up with this language, the Easy language. And now let's see what the language has to offer. We have all the basic features, and these are the main features that are supported by the language. It supports the use of functions. It can have multiple parameters, and it can also be called recursively. And we have also made sure that the scope of the variables in different blocks are handled perfectly. And we've also handled basic exceptions. We've supported nested ifs and nested loops, and we also supported ifs inside loops and vice versa. We've also tried to decrease the runtime of the code to a certain extent, and we also allow users to input values to the program, and we also write to the console, which also includes writing strings to the console. Oh yeah. And this is the grammar of our language, which starts off with the program block that contains the statement lists. The statements are declaration statement, assignment statement, read statement, write statement, and so on. And we have made it quite simple, as the declaration statement, as you can see, is just use the variable keyword and give a name to it, and that's all. Your variable is declared, and to assign something to that variable, you'll just have to give its name and equate it to an expression or a value. And as I said before, we have supported read statements to read from the user, and we also support write statements to write to the console. We've supported if else case, loop statements, function blocks, and return statements. We've also handled the basic expressions like addition, subtraction, multiplication, etc., while keeping in mind the precedence of the expression. We've also handled conditional expressions like equal to or less than or greater than, and so on. We've also supported comments. And yeah, to summarize, these are the statements that we support. And now Pratik will give an explanation about the compiler part.
Hi, this is Pratik and I will explain the compilation flow of our project. So in compiler, we have three components: lexical analyzer, parser, and intermediate code generator. So this is how the compiler flow looks like. We are providing the program file as an input, then we will be performing lexical analysis on it. Then there is step of parsing that output given by lexical analysis, and we'll be generating the intermediate code. So in lexical analyzer, we are providing input as program files, and what lexical analyzer does is that it breaks down the program into the list of tokens. This list of token will be sent to parser. So in parsers, when we get this list of tokens, it's generating a parse tree based on the grammar. So what parsing steps is needed to do is it checks for the flow of execution. So this is how a sample parse tree looks like for the given sample code. We are declaring a variable x and y, and then performing this execution on these operations. And we have also handled the precedence here. So in intermediate code generator, we are getting parse tree as an input, and what it does is that it will generate a bytecode from this input parse tree. So for this sample code here, we are declaring variable x and variable y, and in the intermediate code here, you can see that we have the CLX, which is a declaration of x and declaration of y again. Then since we are using stack based models, we are pushing those values of 2 and 3 onto the stack, performing the multiplication, and so on. It will execute the and generate the intermediate code. So this is how the actual code would look like. For compiler part, we are getting a char stream, which is our input program file. Then using lexer object, which is it is getting converted into the token stream. This token stream is later then passed, and what we get here is a parse tree, which would again will be provided to the intermediate code generator, and then we'll get our intermediate code. Next part will be explained by Ram.
Hi, I'm Ram. I'm gonna explain about the code architecture of our project. Let's first see the code structure of our compiler. So, easy compiler, this is our main class in our compiler part. So it gets a file name as an input and reads the file name and then pass it on to the lexical analyzer, and which generates the token stream, and this token stream is passed on to the parser, and the parser generates a parse tree which is passed on to the intermediate code generator. This intermediate code generator generates the intermediate code. Let's see the logic behind this intermediate code generator. So this is our intermediate code generator. The main variable in our intermediate code is an array list. So this array list stores the intermediate code line by line, such that each index of the array list is a line in the intermediate code. So whenever the parse tree visits a node, an enter statement for that node will be called, and whenever the parse tree exits the node, an exit statement will be called for the corresponding node. So here, for declaration statement, whenever a parse tree visits a declaration statement, it will call this enter declare statement. In this, we'll just add a keyword declare and the identifier that has to be declared. These keywords are already defined in our constants as easy constants, which can be both used in the intermediate code generation and the same can be used in the runtime code. So in intermediate code generator, so like this, for each node we visit in the parse tree, we'll have a particular action. So these are the following functions which writes the intermediate code. In this, we have a nested stack, which is used to handle the nested conditions. So here in if statement, whenever an if node is visited, we push the nested count into the nested stack and append it to the label. Same way, when the if node is exited, we'll pop the nested stack and append the number to the end if. Same way, we also handle this for the loop. Here I will show you an example how this is handled for a nested loop. So this is a basic nested loop. Here we have two loops and the corresponding intermediate code, here it is. So this is the first loop. It has a loop keyword and the number appended to it. Same way, the inner loop has a keyword loop and the number 2 appended to it. So this is an end loop for the inner loop. So 2 is appended here and the outer loop 1 is appended here. This is how we match a nested loop. Let's next check how we execute our program. Easy Executor is the main class in our runtime. So this file takes file name as an input and reads the intermediate file and adds each line to the code list array list. So each line is an element in our code list. Here we also use iterator index, which maintains the control flow of our code. Based on the keyword in the intermediate code, we perform the actions. For example, if we come across a declare keyword, we declare the variable and store the variable inside a variables hash map. This hash map will store all the variables in our program. In addition to this variables, we also have instack and boolstack. Instack maintains the current integer values in the stack. Same way, boolstack maintains the current boolean values in the stack. Here, I'll show an example of simple addition. So this is a code for simple addition, and the intermediate code will be as follow. So it will load the variable x and it will load the variable y. Both of these are pushed into the stack and then add operation is done. So in execute, and when it comes across a load keyword, it loads the variable from the variables hash map and push it into the stack. Same way, it loads two variables. When an add keyword is encountered, it will add the last two elements and push the result to the stack. So next, when an assign statement is encountered, it pops the stack that stores the value in the variables hash map. So we have a stack called stack trace, which maintains the function call. same as Java or C, C++. Whenever a function call is called, that index will be stored in the stack trace. So, using this, we have handled the recursive function calls. This stack trace is popped when a function ends or a function returns a value. So, this is how we handle the recursive calls. We also have something called scope. This scope is maintained differently for different functions. These are also maintained for the recursive functions. Now Manoj will show you how our program works in real time. Thank you.
Hi, I am Mohan Yadav and I'm going to walk you through how our code works.
So let me show you the list of sample programs which I'm going to run today. So these are the sample programs, and among those I'm going to run 4 unique files which have unique functionalities in them. So let me begin with the simple addition program. So let me show you the sample file first. We have an extension easy for a file stored based on the grammar. So this is how some program looks like. We are getting 2 variables, we are reading it, and then we are adding it. So in order to run this, we need 2 jar files. One is compile time and other is runtime. So let me show you the command for that. So once this command is executed, let me show you how the intermediate code looks like. The intermediate code is generated at the same location as the easy file, with the same name, but it has an extension called easy I, which represents the intermediate code. So this is how our intermediate code looks like. So let me show you the runtime for this. For the runtime, we have to run the sum.easyi file, and we have to give 2 inputs, let's say 5 and 6, which gives us the input 11. So next, let me show you other program which is nested if. First, let us look at the code. So we have implemented a if, and then we have implemented nested if inside it. So let me run this and show you the output for this. And after the runtime execution, we have implemented a simple nested loop concept inside it, and as you could see, the expected output in that. So let me show you next the loop implementation. So after the compile time, let me show you the runtime for this. So let me run the loop 3, and yeah, so as you could see, we have nested loop implementation. So for that, we are running it 2 loop inside. The first loop has a value 3, and we are incrementing it till the value less than 3. So it is 0, 1, 2, 3 times, as you could see the output for this. So next, let me show you function implementation in one of our programs. So we are calculating power of a particular number. So let me calculate the power of 2 to the power 5, which gives us 32. Let me explain you the functionality implemented in this particular program. So in this particular power function, we have implemented first a function, and then we have implemented a recursive function inside it. And along with recursive function, we have implemented functions with multiple parameters, as you could see, multiply of a and power of a comma b minus 1. And we have also implemented two functions in the same program. So these are a 4 Unix program which a compiler supports. And for the future scope, a compiler can support lists, multiple data types, and also data structures. Thank you.